Hello everyone, welcome back to our course on memory device technology for AI/ML computing. So today is the concluding lecture for NAND flash, but before that, let's do a brief overview of what we were discussing the last time around. We saw how bit scaling is done in modern day NAND flash by programming intermediary threshold voltages. So basically, we can fit in more bits by having several threshold voltages in the same physical cell. So this can also be called bit scaling or logic scaling. We also saw that we had three different kinds of NAND flash cells: MLC, which stores 2 bits, TLC, which stores 3 bits, and then we had QLC, which stores 4 bits. What I hear is there is a lot of research happening for 5 bits and also 6 bits. Also, we saw that bit scaling comes with its own set of challenges. There are no free lunches, as I say. While cost per bit really improves drastically, it causes problems in reliability, something that we will discuss in detail today, and also performance. Both reliability and performance suffer when we go from SLC, MLC, TLC to QLC, right? And the primary reason for that is that your noise margins are reducing, and also to do more programming of threshold voltages. As you can see in this schematic itself, this schematic, it takes more time to do both program and read. Okay. Also, we saw the schematic for incremental step pulse programming, which ensures faster programming with tighter VTH controls, both for fast and slow cells. Also, remember what was the intuitive reason why ISPP works? With the analogy of filling an air balloon, right? The consequent blows that we have to give into the tire or the balloon has to be higher in magnitude. Okay, so let us begin today's class by first celebrating the tremendous success both in the aspects of dimensional scaling and bit scaling in 2D planar NAND flash. Then we will see what are the challenges. As you can see in both these graphs, both dimensional scaling. So we started NAND flash commercialization long time back, but just in 1 decade, as you can see, you move from 160 nanometer to the 24 nanometer. So this is just a story about dimensional scaling. So this figure also talks about bit scaling. You see bit scaling from SLC, MLC, TLC to QLC. Both of this together helped us achieve almost 100x improvement in die capacity or memory capacity in just 1 decade. In just 1 decade, you were able to go from 1 GB to 100 GB. However, if you look at this graph very carefully, you will see that it is also very clearly evident that post 2010, the total die capacity has saturated. So you are not really able to push the die capacity to more than 100 gigabytes. So what is the main reason why there is a saturation in the capacity of the 2D NAND flash cell? If you want to answer the question in just one word, the one word is reliability. What is reliability? Reliability is more like an umbrella term. It is to indicate or encompass any effect that leads to a loss in data or a corruption in data. Needless to say, reliability becomes a very important metric, especially when we move from memory to storage devices. Therefore, we will specifically focus on the issue of reliability in this class. Okay, we will see also that reliability will get worse as we do both dimensional and bit scaling. So here I have indicated 4 key reliability challenges for 2D NAND flash. It is endurance, retention, cross interference, and the few electron problem. While the first 3 problems are universal across all non-volatile storage devices, the few electrons problem is particularly NAND flash specific. Okay, and also it is important to know, as we will see very soon, the cross interference and few electrons problem is what is going to create the major issue, or it is going to be a showstopper when it comes to 2D NAND flash scaling. Okay, so let us begin with the first reliability challenge. The first reliability challenge is endurance. So how do you define endurance? Endurance is nothing but the number of read-write cycles, or in flash terminology, number of program erase cycles that you can perform before your memory window collapses. What is the meaning of collapsing memory window? It means that the threshold voltage for program state and for erase state become almost similar, or they get close to each other. So in both of these graphs, what you can notice in the collapsing or reducing of the memory window is that the erase state is more affected. It is more adversely or predominantly affected. To understand why that is the case, we need to look at the microscopic mechanism. What is the microscopic mechanism which is causing an endurance problem? So this is what I have indicated through this very simple band diagram. So what happens is, as you do several program erase cycles, there is a lot of stress that is created in the tunnel oxide. And because of the stresses created in the tunnel oxides, there are defects which occur in the SiO2, which is generally of the nature of oxygen vacancies. So what ends up happening is these electrons go and sit or get trapped in these defect sites, which are generally within the band gap of SiO2. And as a result, since these electrons, which were earlier free carriers, get trapped, the flash cell, you are not able to fully erase. You are not able to fully go to the lowest threshold voltage, because some of the traps are always permanently stuck inside the tunneling oxide, right? A very beautiful work here by K. Mai's group, who is from Carnegie Mellon University. They had shown that there is a adverse, very, very adverse effect in endurance. You see, this is the number of PE cycles. As the number of PE cycles increase, the variability in the endurance becomes a very big issue. The threshold voltage gets spread out more and more as you subject to more number of PE cycles. For what? This is for a highly scaled 2D NAND flash MLC. That is why you have P1, P2 and P3 states. So this is the first reliability challenge. The second reliability challenge is called retention. What is retention? Retention is, suppose I store some bit into the flash cell. How much time does that bit get retained, or how long after the bit has been stored can I can read out without seeing any loss. So as you can understand, because in a flash cell, the primary mechanism of storing bits is through trapped charges, the loss of retention is also caused by the loss of electrons, just like was the case even in the DRAM storage node. So when you store some electrons, there is a chance that they may dissipate out into the surrounding environment. But here it is little bit different compared to DRAM. Why? Because remember, this was your charge storage layer. The charge storage layer in both the sides was protected by oxides. So you may wonder, how is this charge leakage happening? It is happening again because of the defects that are created when you do multiple PE cycles. When there are defects that are created, a new mechanism other than direct tunneling and Fowler-Nordheim tunneling, a new mechanism called trap-assisted tunneling comes into the picture. In trap-assisted tunneling, what essentially happens is electrons can hop from the charge storage layer into intermediary traps and then go off into the substrate, right? So this is the primary mechanism in the floating gate transistor, in the 2D floating gate transistor. However, the story for the 3D transistor is slightly different. In the 3D transistor, what happens is the storage layer is no longer the floating gate. It is your charge trapping layer. And as we will see very soon, the charge trapping layer is shared across different word lines. There is no isolation, just as is the case in the 2D floating gate transistor. Therefore, if some charges are stored in one word line, there is a chance that they might leak out laterally also. This is called lateral charge migration, and it is a very big problem for charge trapping transistors generally used in 3D NAND. Okay, so generally the definition for retention is that your non-volatile operation or storage is valid for 10 years. That means once you store a bit for 10 years, it should hold. But how can we release technology if we wait for 10 years to see whether a bit is holding or not? So what we do is something called accelerated testing. What is the main philosophy of accelerated testing? It is very simple. You apply more strain to the system or more stress to the system in form of electrical strain and in form of elevated temperatures to see whether the storage can happen for a few weeks, and then you extrapolate the results to 10 years. So this is the first form of stress you apply. What you are checking is what is the data retention time across the PE cycles. Remember why PE cycles will affect your data retention? Because more the number of PE cycles, more are the traps that are introduced in your tunneling oxide, and lesser will be your retention. Okay. Next, what you do is you elevate the temperatures. For example, generally the industry standard is to have the 10-year storage at 85 degrees. So in this experiment, what they have done is they have subjected it to more elevated temperatures like 150 degrees, and they have also checked it at room temperatures, and they see that even at elevated temperatures, if you see, they have done the measurement only till 10 to the power of 4 or 10 to the power of 5 seconds. And then through dotted lines, they have done an extrapolation to check that the memory window still holds after 10 years or till 10 years also. So the third reliability challenge is known as cross interference. Now remember, cross interference is something that we had also seen in the DRAM cell. Try to recall, we saw how row hammer effect happens in DRAM cells when you try to scale DRAM cells because of the cross coupling between word lines and bit lines. But in flash transistors or in flash arrays, there is an additional coupling of floating gate to floating gate. Because remember, the floating gate is also a capacitive element. So this capacitive coupling is what creates the cross interference in our NAND flash arrays. So people do extensive studies. They look at the victim word line and they check how a particular cell is affected when neighboring bit lines and word lines. First neighbor, second neighbor, when they start operating again and again, just like in the row hammer effect, what happens to the VT shifts in the victim cell? And what people have found out essentially is that as you reduce technology nodes, as you go from 100 nanometer to close to 20 nanometer, the cell to cell interference increases from roughly 1% to more than 40%. And it has been shown, especially in this particular paper, again by CMU, that in 20 nanometer 2D NAND flash cells, the shift in the threshold voltage could be close to 40% if all the neighboring cells are continuously being programmed. Now, this is a major issue, and that is why I had said cross interference effects will lead to one of the reasons, will be the Achilles heel, or will be one of the main reasons why it will be difficult to scale 2D NAND flash beyond 20 nanometer node. The final and the most important reliability challenge is called the few electron problem. So what is this few electron problem? It is very easy to understand. When you are reducing the overall dimensions of your 2D NAND flash cell, you are also reducing the dimensions of your floating gate. Now remember, the floating gate is the most important functional layer. So as you reduce the size of the floating gate or the volume of the floating gate, the number of electrons it can hold will also reduce. This is the graph which is indicating this idea. So at the 90 nanometer node, each floating gate could hold roughly 1000 electrons. However, in the current 20 nanometer node, this reduces to less than 40 or 50 electrons. Now this is a very big issue. Why? You can understand this is a big issue because too few electrons will really adversely affect all your reliability problems. The fluctuations in VT because of loss of a single electron will be much large if you have just 50 electrons compared with 1000 electrons. Let's consider a floating gate having 100 electrons, 1000 electrons and 10 electrons. So if one electron is lost in a floating gate with 1000 electrons, it is a VT shift of just 0.1%. For 100 electrons, it will be 1%. But for 10 electrons floating gate cell, the difference in VT will be almost 10%. And this is what causes very poor retention when you start scaling down the 2D floating gate transistor. And this is what is really indicated in these really alarming experimental results. What they have found out is that in a 35 nanometer NAND flash cell, because you have only 200 electrons per bit, the average retention time drops to only 3.3 years. Okay, and as you can understand, because VT margins are smaller, when you go from SLC to MLC, it will cause even bigger problems when you go to MLC or 2 bits per cell. As you can see, for the 35 nanometer node, the retention time for a 2-bit cell drops to just 1 year. So when it drops to 1 year, can you even call it a non-volatile memory? Not really. Therefore, people realized that scaling the 2D NAND beyond 20 nanometers is almost impossible. So then we started looking for solutions. The only solution is to keep increasing the cell area and therefore more precisely the number of electrons. Keep increasing the number of electrons without increasing the footprint. So do you have any ideas inspired from modern day city planning? So the idea is to scale in the vertical direction. And this is how you transition from 2D to 3D NAND flash. Just like in cities, real estate is very expensive. So you accommodate more and more number of people by constructing tall skyscrapers. Similarly, when you transition from 2D to 3D NAND flash, you improve the bit density by using vertical scaling. Let us understand how this is done. So what we will do is we will focus on 4 key differences which enables the transition from 2D to 3D NAND flash. The first important difference, as you can see in this particular figure, is that the lateral string, remember the lateral string was in XY direction for the 2D NAND flash. This 2D lateral string and the direction of flow of current was also laterally. As you can see from the schematic, this completely changes. You make the lateral string sit on its tail. And as you can see in the right at the top of this building or skyscraper is your SSL transistor, and at the bottom is your GSL transistor. And all these are your individual control gates. So the first thing you do is very simple. You flip the 2D string into a vertical 3D string. So current also, the string also becomes vertical and the direction of string current also becomes vertical. Okay. The second major alteration that you do is you completely change the transistor architecture from planar 2D architecture to gate all around 3D architecture, as you can see over here. So this is your planar 2D architecture and this is your gate all around architecture, a cross section of which is shown over here. Now this is a very, very big change because Planar transistor only controls one particular surface, whereas gate all around wraps around. It completely wraps around the channel. Why is this major change made? There is couple of very, very important reasons, and that we will try to understand next. So this is a schematic of your planar 2D transistor, which is used in 2D NAND, and this is a cross section of the gate all around transistor, which is used in 3D NAND. So as you can understand, the reason why even you are going from planar architecture to gate all around transistor architecture in transistor design, in logic transistor design, is because gate all around architecture gives you much better electrostatic control. Why does it give you electrostatic control? Let's understand it intuitively. Try to imagine controlling the flow of water in a dam fashion by having a lateral shutter or a vertical shutter versus controlling the flow of water through flowing through a pipe, through pressing through the pipe. Of course, it is very intuitive to understand. When you try to control from all the sides, the control of the particular flow of water will be much better. Similar is the case with the flow of current also. That is why gate all around architectures give you much better electrostatics control. But that is not the only thing. You can also have a much larger channel area. Why can you have a much larger channel area in gate all around transistor? Because you can literally relax the critical dimensions from close to 20 nanometers in 2D to more than 100 nanometers for a gate all around transistor. This is because, see, in planar architectures, you are very sensitive about the lateral area, which is the real estate. In gate all around, because you flip the string, you don't really care how big this is. It will only increase your vertical dimensions. It will not increase your lateral dimensions. Therefore, you are less sensitive about the amount of area each cell is occupying. And as we see, the channel area in gate all around transistors can be 20 times that of your planar transistors. And the big difference here is it can store more number of electrons. It is seen that for advanced technology nodes, per VT shift, per one electron VT shift, while gate all around transistors can accommodate 250 electrons, your 2D NAND flash only can accommodate 30 electrons. And as a result, by going from planar to 3D, you essentially solve the few electron problem. That is also the reason why it suffers from much lower interference effects. So this is the key reason and a big change from 2D to 3D, going from your planar cell to your gate all around cell. Now let's discuss the third and probably the most important change. The most important change is transitioning from the floating gate architecture that we have been continuously studying about to the charge trapping model. Why do we use the charge trap cell in 3D architecture? Let me tell you. Actually, the floating gate has much better reliability characteristics compared to even the charge trap cells. So what is the reason still to move from floating gate to charge trap when we go to 3D? The real answer lies in what is the charge storage layer in charge trap versus floating gate. Let us remind ourselves, the charge trap had a charge storage layer of silicon nitride. Now silicon nitride is an insulator. What is it in case of floating gate? It is doped polysilicon, which is a metal. Therefore, while floating gate transistors have to be isolated, see, they have to be isolated from its neighboring cells with an interlayer dielectric. This is your first floating gate, this is your other floating gate. Because both are metals, if you store some charges over here and you don't have any isolation, it will directly percolate or directly diffuse into the other floating gate. Therefore, in floating gate architecture, where the charge storage layer is a metal, it is absolutely mandatory to have isolation from the neighboring cells. Whereas in the charge trapping cells, that is not the case. And this gives a very distinct advantage when it comes to cost and scalability in the 3D NAND architecture. This is because, as you can see in the charge trapping cell, the charge storage layer is common across different word lines. There is no need to go to isolations between the two word lines, and therefore many process steps which are required to create these isolations in the case of floating gate can be completely avoided in the case of charge trapping transistor. And this really helps in improving cost, and cost per bit is the main metric that all your companies care about. Okay. Or the second important aspect of using charge trapping is because this isolation is not required. As you can see from the schematic, you can make them smaller. You can keep the cell sizes even smaller, and therefore scalability is also much better in the 3D NAND flash era, which charge trapping as compared to floating gate. Finally, we go to the fourth important aspect, that is transitioning from a 2D block array architecture when we deal with 2D NAND flash to a truly 3D block array architecture. Remember, when we were studying 2D NAND flash, the block was essentially two-dimensional storage structure. The pages were arranged in rows or word lines, and the columns were your strings or your bit lines. And this completely changes in the 3D NAND flash as seen in this particular SEM image. The data is truly stored in a three-dimensional array, also indicated in this particular schematic. So let us look at this schematic a bit carefully. As you can see, marked in green is your string, which is organized in a vertical direction. Okay, this has a common bit line. The string has common bit line, whereas the page now is arranged in a 2D plane, or is this 2D slice as indicated by this pink shading. Now you may feel initially that this particular cell and the neighboring cell has the same bit line and the same page. So how are you ensuring that unique data is stored? This is done because they are in fact differentiated by different select lines. So by selecting different select lines, you can take a combination of separate string and separate page. Therefore, as you can see, data is stored in a truly three-dimensional fashion. Finally, we will discuss about the scaling trends in 3D NAND, which is very different from scaling in 2D NAND, because what is happening is vertical scaling, as you can see from the roadmap of a very popular company, Kioxia, which is one of the major manufacturers of NAND flash. And as you can see, only in very few years, in 2016, they had come up with the 48 layer NAND flash, and within just a few years, they have gone to 162 layer NAND flash. And what I hear from my friends in industry is that Micron has already released 276 layers, and Samsung has promised more than 300 layers by this or the next financial year. Okay, so in summary, this vertical scaling has what enabled NAND flash into a new era of truly three-dimensional scaling. And as you can see from both these schematics, although you are able to relax the critical dimension rules, what you are able to make the size bigger and bigger, you are able to integrate more and more bits into the same footprint. Of course, all of this is possible only through very large advances in nanofabrication technology. With this, we conclude our study of NAND flash, and this is a good time to celebrate. This is a nice time to reflect, to pause, and also to celebrate, because we are more than half through our course. So just want to bring out our motivation slide just to reorient ourselves. We have finished the first part of our course where we have covered the advances in current memory and storage device technology. We looked at the von Neumann architecture, the memory hierarchy, the array architecture, and spent quite some time looking at SRAM, DRAMs, and NAND flash. This forms the core of current modern day technology. Moving forward, we are going to look at more futuristic opportunities, how electronic non-volatile memories, which are also called storage class memories, can really solve the so-called von Neumann bottleneck. Thank you very much. See you in the next class.